Dear students, today we'll see what do we mean by FET, that is field effect transistor. So here we see the topic is FET, that is field effect or transistor, or it is also called as JFET, that is junction field effect transistor. Now actually if you see the classification of FET, FET can be mainly classified in two types. One is JFET and another one is MOS FET. Whereas JFET is most of the time also referred as FET. Okay. So here we'll first see what is a JFET today. And in this we are going to see first what do we mean by that field effect word meaning in that field effect transistor. Second, we'll see types of field effect transistors. Then we'll see a construction of FET. Then we'll see a working of FET. Then we'll see applications of FET. So here, whenever we are referring FET, that means we will be seeing about the JFET, that is junction field effect transistor. So to start with, we should have a background of it, how FET structure is formed and how it is going to work. So based on that background, then we can go on seeing the other definitions. Okay, so FET will be having a main structure as a bar. Say there is a bar, this is a bar. Now let's take a bar of n-type semiconductor. This is a bar of n-type semiconductor. Okay, so this is a bar of n-type semiconductor. We can also have a bar of p-type semiconductor. But here we will consider one example for n-type semiconductor. And in this n-type semiconductor, in this two sides, p-type semiconductor induced. Okay, so p-type semiconductor is induced in the two sides as shown in the above structure. Now here you are having p and n, so you will be having a p-n junction and there will be a small depletion layer here because this you have formed a p-n junction here, and similarly on the other side also you will be having a small depletion layer here where you will form that p-n junction. Okay, so there will be a small depletion layer because there is a junction formation between p and n, and we know how a depletion layer, a potential barrier is formed when we studied the theory of p-n junction semiconductor diode. Now here with this structure to the bar, in this case we have considered n-type semiconductor bar. So we will have one terminal here and one terminal here. Okay, both these terminals can be interchangeable and these terminals can be named as, say for example, we will take this down terminal as source and the above terminal as drain, and we will have one terminal here which will be connected to the p-type semiconductor, which will be internally connected to the other p-type semiconductor also. Okay, so and this terminal will be called as gate. Okay, so we have source S, drain D and gate G. These are the three terminals of FET. Okay, now here if you see this n-type bar, now in this n-type semiconductor the majority charge carriers will be electrons. Okay, so we'll have this electrons, many majority charge carriers we can show here as electrons. These electrons, if I want to make them flow from source to drain, so if there is a meaning for the source, that means the source is going to emit electrons and the drain is going to collect electrons. Same like your BJT. In BJT we had emitter and collector. Like this only in FET now we will have source and drain. So I want to make source as a emitter of the majority charge carriers, which is going to emit majority charge carriers, and I want drain to collect majority charge carriers, and for that purpose I should be able to connect a proper polarity voltage source to it. So here if I see, if I take this terminal and if I take this terminal of source and drain, now here at the source I want to repel electrons. Okay, so here source I want to repel electrons, so this will be the source point, I want to repel means I will have a negative polarity of the battery. Okay, so I want to repel electrons. So electrons should move from source to drain like this. If I want the drain to collect the electrons, then I should have a attractive polarity of the battery here. So this will be positive. This will be positive. So here positive, negative. So if you want to show some more cells here, you can show negative, positive. Okay, now this will be better. Now this is your voltage between drain and source, and the polarity of the voltage is such that negative polarity is connected to the source, so that this can repel the negative charge electrons towards the drain. So the electrons will start moving towards the drain, and at the drain is connected to positive terminal of the battery, so that electrons are attracted here, so that we can show a flow of electrons through this passage from source to drain. Now this passage will be called as channel. This will be your channel in which the electrons are going to move from source to drain. So this is your channel. Okay, now here the width of the channel, that is this part, the width of the channel can be increased or decreased depending upon the depletion layer between this p-n junction. So here we will give a negative reverse bias voltage to the gate terminal. Now gate terminal is connected to p-type semiconductor. So if you want to make it a reverse bias, then you connect negative of a battery, and positive of a battery will be connected back to this source terminal. So here you can have negative and positive. So this will be the voltage between gate and source, and it will see that the depletion layer of the p-n junctions on both sides will increase if you increase this negative voltage or this reverse bias voltage which is applied to the gate. So what will happen is, initially the channel, if it is like this, say this much is your bar, this is the n-type bar, and this is your p-type semiconductor, and this is a small depletion layer. Okay, so here you have still not increased the voltage VGS. Now after you increase the voltage VGS between source and gate, so here minus plus, so this is your VGS, this is your gate, this is your source. If you go on increasing this VGS applied voltage reverse, so this layer, this depletion width will go on increasing. This depletion width will go on increasing, and this channel where the electrons are going to flow becomes narrow. That means the flow of majority charge carriers between source and drain will decrease, and that's why the drain current, that is the output current in the circuit, will decrease. That means as we increase the reverse bias voltage, you can decrease the current, and as you decrease the reverse bias voltage, you can increase the current. So with this input voltage, this electric field, you can control the current which is flowing from source to drain, which is called as output current, which is called as drain current. Now this current which is flowing from source to drain can be controlled by this input voltage. So it is called as voltage control device, or it is called as field effect transistor. So that is how the name comes, as field effect transistor. It is a voltage control device, and a current which is going to flow from source to drain will be of only one type of charge carriers. Say for example, we are using a n-type semiconductor here, n-type bar here. So we will say that electrons are going to flow from source to drain. Okay, if you use similarly p-type bar, then you can say holes are going to conduct from source to drain. So if you show a p-type bar, you can also show a p-type bar like this. Now you can have a p-type bar also. This is p, this is p, and in that on both sides here you will have n-type semiconductor, n-type semiconductor, and you will have this p-n junction on both sides. So this will just be the opposite construction structure, and to which different types of voltage polarity should be applied, so that the majority charge carriers in the p-type semiconductor bar, that is holes, they flow from source to drain. So this is a concept what you have to remember before going into all the definitions and concepts of field effect transistor. Okay, so here let's start now with this background. And here you can see I have shown a circuit. Now in this circuit, again, we have taken an example of N-type bar, and there are two P-type semiconductors on both sides. So here you are having your N-type bar. Okay. Now this is your source terminal. This is your drain terminal. Your electrons are going to flow like this from source to drain, and the direction which is shown over here, this is for a conventional current, that is positive current, which will be opposite to that of electron current. Okay. Now here you have connected this supply voltage such that this negative polarity will repel the electrons from source, and here this positive polarity will attract the electrons from the drain. So electrons are going to flow from source to drain, and here you are going to apply a reverse bias voltage. So because this is P-type semiconductor here on both sides, so here we will apply a negative supply of the battery, and then here we'll have positive, negative, positive. Okay, so positive. So here this will make this junction over here, which is internally connected to both the P-type semiconductor, as reverse bias, and this depletion layer will go on increasing if you increase the reverse bias voltage, that is VGS. And because that depletion layer increases, the flow of electrons between source and drain will decrease, and hence we say the current flow through the FET decreases if you increase the input gate to source voltage. And if you decrease the input gate to source voltage, the current which is flowing from source to drain will increase. So it is having an inverse relationship. So the input voltage is going to control the output current. So here also we have shown an N-type semiconductor bar in which two sides P-type semiconductor are induced. Okay, we can also have a P-type bar, and in which you can induce on two sides N-type semiconductor. Okay, so here let's start with the definition of FET. Now the field effect transistor FET is a three-terminal active device that uses an electric field, as I have told you, to control the current flow, and it has a high input impedance which is useful in many circuits. Okay, so it has high input impedance because your input, you are going to do a reverse bias at the gate, and the gate source voltage which you will be having, that electric field, that voltage is going to control the current which is going to flow between source and drain. So here this is the definition for FET. Then if you go to see types of FET, then FET, as I have told you, FET can be classified mainly as junction FET, this is JFET, and insulated gate FET, which is your metal oxide semiconductor FET, MOS FET. Okay, now a junction JFET can be further divided into two. Okay, then those two will be your P-channel JFET and your N-channel JFET, and both work in depletion mode. So what is this depletion mode and enhancement mode? You will come to know when we actual study what is MOS FET. In that we can show what is depletion mode and enhancement mode. Now here we can remember that JFET is basically of two types. One is P-channel JFET and one is N-channel JFET. And this JFET only here we are going to refer as FET. And if you see the MOS FET classification, you can have depletion type of MOS FET, enhancement type of MOS FET. Again, in a depletion, you can have P-channel or depletion type MOS FET. You can have N-channel or depletion type MOS FET. Then you can have P-channel enhancement type MOS FET. You can have N-channel enhancement type MOS FET. That is, when we study MOS FET, we will see those classification. So here junction FET will be classified in two types, and those two types are called as P-channel JFET and N-channel JFET. This is what we are going to see here. Now here most commonly two types of FETs, as I've told you in the classification. One is junction field effect transistor JFET, and second one is metal oxide semiconductor FET or MOS FET or insulated gate FET. Okay, so here in this lesson today we are going to see what is junction field effect transistor. That is when commonly we refer FET, we refer JFET. Okay, so whenever we speak about FET, we will be referring what is junction field effect or transistor. Okay, and the other main important type of FET is metal oxide semiconductor FET, that is MOS FET. So here then, what do we mean by junction field effect transistor? The functioning of junction field effect transistor depends upon the flow of majority carriers, electrons if you are having n-type bar, or holes if you are having a p-type bar. Basically, JFET consists of an n-type or p-type silicon bar or containing p-n junctions at the sides. Following are the same some important points remember about FET. One is the gate terminal. Now, gate terminal is one which is very important, which is going to control your current between source and drain. So this is your gate terminal. By using diffusion or alloying technique, both sides of n-type bar. Now here we will take an example of n-type bar. Okay, we can also have p-type bar, but here we'll take example of n-type bar. So alloying n-type bar are heavily doped to create p-n junctions. These doped region are called as gate. So as we have seen that, say for example, if you're having n-type bar, okay, n-type bar, so here you will be having two areas where you have p-type semiconductor. Both will be internally connected, and this will be taken as terminal gate. This will be taken as terminal gate. Okay, then what do we mean by the source terminal? It is the entry point for majority carriers through which they enter into the semiconductor bar. And then drain, it is the exit point for the majority carriers through which they leave the semiconductor bar. Then what is a channel? It is the area of n-type material, because here we are speaking about n-type bar. We are saying that n-type material through which majority carriers pass from source to drain. If you speak about p-type bar also, it is the same logic. There are two types of JFETs commonly used in the field effect semiconductor devices. They are N-channel JFET and P-channel JFET. Now here, if you go to see the structure of N-channel JFET and the symbol of N-channel JFET, it can be shown like this. Now here you can see this is a N-type bar. This is a N-type bar, what you have shown here. This is N-type bar. Okay, and here in this you have induced this p-type semiconductor here and p-type semiconductor here, and here you can have your depletion region between p-n junction. Here also you can have your depletion region between p-n junction, because here p-type and n-type attached together, joined together, will make a p-n junction. Both these p-type semiconductors are internally connected. They are internally connected, and that common terminal is called as gate. And in the n-type bar, one terminal will be called as drain and the other terminal will be called as source. These two terminals can be interchanged. They can be really dedicated as source and drain depending upon the voltage polarity, whatever you are going to connect to them. Okay, and here is the symbol for N-channel JFET. So here you can see you have shown this gate, you have shown drain, you have shown source. Okay, so here you can see this is gate terminal, this is drain terminal, and this is source terminal, and this is the symbol of FET. Okay, and here you can have these terminals, and here you can have your gate terminal. Now if the arrow goes inside here, it is N-channel. It is N-channel JFET. If the arrow is in the opposite way, then it is P-channel JFET. Okay, so at present we are viewing what is N-channel JFET. Then if we have to give a theory on N-channel JFET, so here we can say that it has a thin layer of N-type material formed on P-type substrate. Then the gate is formed on the top of the N-channel with P-type material. At the end of the channel, the gate, the lead wires are attached and the substrate has no connection. When a DC voltage source is connected to the source and the drain leads of a JFET, maximum current will flow through the channel. The same amount of current will flow from the source and the drain terminals. The amount of channel current flow will be determined by the value of VDD, that is drain voltage, and the internal resistance of the channel. Now we will see what is P-channel JFET here. So here you can see a P-channel JFET in which you are showing a P-type bar here. So here you can see a P-type bar. So here your holes will be the majority charge carriers which has to flow from source to drain. according to your voltage supply connected between source and drain. Okay, and there is n-type semiconductor here which will form the p-n junction here, and here also you can have n-type semiconductor which will form the p-n junction. Both these n-type semiconductors are connected internally. Okay, and they have a common terminal output called as gate. On the p-type bar you can have one terminal named as drain and the other terminal named as source. This can act as source and drain depending upon what voltage polarity you're going to apply to the two terminals. And here you can see the symbol of p-channel JFET. So here it is same like your n-channel JFET, only this arrow will be going out. If it is going out, then it is symbol of p-channel JFET. Now if you go to see the theory of p-channel JFET, it has a thin layer of p-type material formed on n-type substrate. The gate is formed on top of the p-channel with n-type material. At the end of the channel and the gate, the lead wires are attached. Rest of the construction details are similar to that of n-channel JFET. So p-channel JFET will be having the same logic. Only thing here, the bar will be of p-type semiconductor and the gate induced small parts of semiconductors will be your n-type semiconductor. And if you go to see n-channel JFET, your bar will be n-channel, and the point where you have to have the gate terminal, there you will be having p-type semiconductor. It is only the semiconductor material what is going to differ, whereas the logic remains same. So here when we go to see what is working of JFET, so here you can see you are going to connect a reverse bias connection to this gate terminal as I've told you earlier. So when you're connecting it to a p-type semiconductor, we can have a negative of the battery here, positive, negative, positive. Okay, so here negative of the battery is connected to p-type semiconductor. So here this depletion region here, we can control the width of the depletion region. So if this voltage goes on increasing, the width of the depletion region will go on increasing, and if the width of the depletion region goes on increasing, the current which is flowing between source and drain will decrease. Okay, so when this voltage applied is minimum, the channel width is more current is flowing between source and drain. But when this voltage increases, the channel width will be less because the depletion layers will increase here. So as these increase, okay, as this increase, the channel where the charge carriers are going to flow, okay, that will decrease and less current will flow. Okay, so this is how it is going to work. That is, input voltage is going to control the output current, and that comes under your working of JFET. Then we'll see what are the advantages of JFET. The JFET has high input impedance because that input, that what you are going to apply at the gate terminal, you are going to reverse bias it, so it will be having a high input impedance. The JFET can be fabricated in small size area. It is a majority charge carrier device, hence it has less noise. It is a low power consumption device, which is very important. It can be fabricated in small size area. It occupies less space in circuits due to its smaller size. It has a negative temperature coefficient of resistance, so they possess higher temperature stability. Then if you go to see disadvantages of JFET, the main disadvantage of JFET is the relatively low gain bandwidth product. Second one is the performance of JFET goes down as frequency increases due to feedback by internal capacitance. So here students, we'll see what are applications of field effect transistor. So number one, FET has high input impedance and low output impedance. So it is used as a buffer in measuring instruments, receivers. Second one is FET has low noise operation. So it is used in RF amplifiers, in FM tuners and communication equipment. FET has low input capacitance. So it is used in cascade amplifiers, in measuring and test equipment. Since FET is a voltage control device, it is used as a voltage variable resistor in operation amplifiers and tone controls. FET has low inner modulation distortion, so it is used in mixer circuits, in frequency modulation FM and TV receivers and communication equipment. Since it has low frequency drifts, it is used in oscillator circuits. FETs are used in low frequency amplifiers, in hearing aids and inductive transducers as the coupling capacitor is small. Since FET occupying less space and easy to fabricate, it is used in digital circuits, in computers, LSD and memory circuits. Thank you, students.